Suppose V be a real vector space. And VC be its complexification of complexification. Okay. Now, whenever you are talking about complexification, your terms are so this induces standard embedding. What is that? What is that embedding? Which embedding I am talking about? Standard. That means, what is your VC? VC has been chosen to be a direct sum of V with itself. Right? Now, if you recall the construction of C as a field, then we have seen that there is a map from R to C. Right? What is the map? If you take any real number A, then we have chosen the map to be A comma G. And this is a standard embedding. Right? Why it is so? Because this map uh, is additive, right? Because A plus B will be mapped to A plus B comma 0, and which is A comma 0 plus B comma 0. Secondly, if you take any two real numbers A and B and take their product, then this AB will be mapped to AB comma 0, right? And this will be A comma 0, B comma 0, because as per definition of complex multiplication. Okay? I'm just talking about complex multiplication. So A comma 0 product with B comma 0 will be AB comma 0. And also this map is one more. Okay. So what we have seen in the field of complex numbers, that R has been embedded as a subfield, right, with respect to this natural entity. And yesterday we have seen that C is a complexification of C as a complex vector space, right? Is a complexification of a real vector space R. So that is, you can represent C as a direct sum of R with itself, which is equipped with the usual addition and the complexified multiplication, which we have seen earlier. Right? So in this example, what we have been noticing is that this map is emerging out as a standard embedding from the real vector space to its complexification, because C is a complexification of R, right? So this embedding works, it plays an important role in the theory of complexification of a real vector space. Likewise, if you want to go up in the general case, you will see that, so 1 minute. A phone আসছে 2 minute. Okay. Okay. So I'm just following this sort of notion of standard embedding of a complexification of a real vector. So here VC is the complexification of V of the real vector space V. So you can choose. So you can define the standard embedding. I'm just following the previous construction, previous definition of standard embedding, which has been set in the case of uh, with respect to following the same definition. So embedding, which is V to VC, right? So let us take in small here. I'm just taking magic, right? So you can check that if you take one plus V2, V1 plus V2 comma, and certainly it is going to be V1 comma 0 plus V2 comma 0. Okay. Great. And also, if you take and also if you take the standard, so right, because of so this map is stability. And yeah. So this is so with respect to this map. So this map helps us. We can say that. So okay, if you look at the case, so suppose you take yeah, to say that if EI be a basis of real basis of V, as EI comma will be complex basis of complexification. C of get it? Because we are just mapping EI to EI comma C. It's a standard end. ঠিক আছে তো? Okay. Also here, if you look at the map, so also you see that suppose you take any real scalar lambda, uh, lambda multiplied with p comma 0. So what is that? Lambda multiplied with v comma 0. So here lambda means lambda is a real number. So that means here lambda plus I0, right? P comma 0. So that means you are taking the matrix which is lambda 0 0 lambda 3 0. Then what will be the situation here? It is lambda v comma 0. So lambda v comma 0 will be lambda v comma 0. Okay. And also lambda 0 comma v. Again, it is lambda 0 0 lambda 0 v. Then with respect to, so what would be, so lambda 0, so this is 0 and this is lambda. That means 0 comma lambda. So for any real number, lambda, this map uh, actually, so it is linear with respect to r, right? Okay. This map, this embedding, this is linear with respect to r. That means r linear. Okay. And also note that this also suggests to think of these kind of spaces, V dx sum with the null vector and null vector dx sum with P. Actually, will we have like V in the complexity BC of, okay. Okay. So this maps to the standard embedding. So this is one. Number two, the standard embedding is actually a early method from V into its complexification. দেখো তো এবার ব্যাপারটা মাথার মধ্যে ঢুকলো কিনা। Okay. And in view of this, one we may think of V Df product with Df sum with theta as the official as a copy of V inside this. We have already seen that R maybe think of R will maybe think of as a copy of, I mean, R comma 0, right here. If you look at this example, this one, so you are just taking the real axis, right? So the members have been chosen to be like having y coordinate 0. So this uh, has been thought of as a copy of R, real line, inside the complex. In a similar way, we're just having the same atmosphere here. V reacts on with theta, we think of as a copy of V inside the its complete situation. Okay, right? And this enables us to treat VC as like the following. VC can be thought of V plus I. Is it okay? As we have already seen, any member from VC can be written as V1, 0 plus 0, V2, that is V1, 0 plus I multiplied with V2, 0. So this has been chosen to be V1 and this is V2. So therefore, V1, V2 can be think of as an object of this form V1 plus I2, right? So that means, so in the simplest way, you can think the complexification of V as V plus IV, right? This will help us a lot. Okay, so let's move forward. Look at the very nice result that we are going to intervene here. So now, suppose we see so this is a complexification of this will be the complexification of a real vector space V, right? So here V is a real vector space. Consider another V the complexification of, you are choosing another real vector space, complexification of another real vector is V dash, right? So that means you are choosing two real vector spaces, right? One is B, another one is V test. And after choosing two real vector spaces, you are being able to construct their complexifications. And definitely this arrow means there is, so you are considering the standard embedding, right? The standard embedding, okay? Suppose let us call it I, let us call it capital I, and this call it I test. So these are standard embeddings. Okay? Now, if you choose any linear map, suppose T. Now here, from V to V dash, linearity means it is R linear because the underlying field is real numbers, right? So therefore, whenever I am talking about a linear map from V to V dash, from in between two real vector spaces, that means we are considering R linear map. Okay, R linear. So our question is, can this R linear map can be taken up to a C linear map from their complexifications? I mean, is it possible uh, to have such TC, which will be C linear here, right? Because these are complex vector spaces. This is a complex vector space. This is also a complex vector space, right? So in between two complex vector spaces, is it possible for you to construct such a TC using the given R linear map T, so that this diagram commutes? So this is the question. So is it possible or not? The answer is yes. And the interesting fact that will be derived uh, just in a couple of minutes. Although we are seeing that this T is a R linear map, and we are constructing another C linear map TC so that this diagram commutes, but their respective matrices with respect to given real basis and complex basis, corresponding complex basis, will be same. Okay, will be same. And I'm just going to give you some familiar examples so that you will get acquainted with this kind of thing. So what is the construction here? Okay, so this I and I test are these standard elements on the respective spaces. Shown in the diagram. Okay. Shown in the diagram. Okay. So what would be the construction? Now, if you want to construct such TC, is a C linear map from BC to BC dash. Okay. So then, what we should get now, if such a series, then what do you have? Then we see that in view of these standard embeddings, right, this I and I dash, you see that if you choose any point in the complexification VC, suppose that it be V comma 0, that means we are taking V from V, small v, so this will be mapped to V comma 0, right? Long I'm just taking any small v from capital V arbitrarily, and then taking its standard embedding, okay, via the standard embedding. I am taking the image of V in VC, which is V comma 0, and that would be, it should satisfy this property that E on this would be V comma 0. Okay? Because we are assuming that such PC exists, that means which will commute this diagram, right? So therefore, so we can have PV here, right? And this PV will be mapped to PP comma 0. Right? Now since this diagram commutes, so this V comma 0 will be mapped to this PV comma 0 under this map TC. Okay. So since we are assuming that such TC exists, then this sort of thing will happen. And this will be true for all small v belongs to capital. Okay. And agreement, what you are having by taking any arbitrary member from the complexification of V. So for any members, so let's call it V1 comma V2, in VC we have then TC V1 comma V2, right? So since we have assumed that this TC has to be linear or C-linear, right? So it has to be something like this. So V1 comma 0, VC 0 comma 1. So that means here it is TV1 just using this above equality plus. Now what is that? The TC of 0 comma V2 can be written as I times V2 comma 0, as we have seen earlier. Now since TC is C-linear, then it will commute with this I. That means TCI V2 comma 0 can be written as ITC V2 comma 0. So it is TV1 comma 0 plus I times TC V2 comma 0. And again we can write down this 1 as TV2 comma 0, right? Okay. And therefore TV1 comma 0 plus, so I times of this member means 0 comma TV2. Just it is stripping the element. So therefore it is TV1 comma TV2. Okay, good. So that means if you are assuming that such TC exists, then you are having such TC which can be represented in this way. Okay? So assuming TC to be a C-linear map from VC to VC dash under the agreement that the diagram commutes, actually you are displaying the map TC, what it should be, right? So it should look like this. TC V1 V2 must be TV1 comma TV2. Okay. So this indicates us how to define TC, right? So we should define. We must define a map TC from VC to VC dash by the rule TC of V1 V2 will be TV1 TV, right? For all V1 or V2 belongs to TC. Okay. What we have shown in the above, we are just checking the construction of TC like the way we have done. Right? We are just following the approach that we have put here. Just by assuming that TC exists with respect to the agreement and the diagram from this. Okay. Now you can check easily that so note that, so we see that number one, what you are seeing that TC is particularly R linear. As because why is R linear? Why is R linear? Because T is R linear, and so therefore TC must be R linear. Right? Why? Because for any real scalar lambda, the TC of lambda V1 V2, right? So what it should be? So it will be lambda V1, lambda V2. Just using the complexified scalar multiplication with respect to lambda to the element V1, right? Although it shows that it is like the familiar scalar multiplication. Okay. Because it is R linear, it is a real number. Because lambda is a real number. So therefore, by the definition of TC, so this will be T of lambda V1 and this will be T of lambda V2. Now since lambda is real and T is R linear, so therefore you are taking out lambda from the bracket on each side. Right? So therefore again having this. So it is lambda TC V1. So therefore it is R linear, right? Now to show that this TC is here, it is not to check that whether this TC commutes with the imaginary unique I, right? Okay. So what would be the situation here? Now recall that we have already seen that to take the scalar multiplication of any element of the complexification with respect to I, then it turns out to be minus V2 comma V1. Okay. Which implies that TC of I V1 V2, this is TC of minus V2 comma V1, right? And therefore it is T of minus V2 P of T1. Now, since T are linear, so it is minus T0. And again, we are getting that point that it is I times TB1, that is I times TC of T1. Right. So that means TC commutes with the imaginary, right? So this implies TC commutes with the imaginary. And therefore, using the previous observation that it is R linear, and using this one that it commutes with the imaginary unit I, you can easily show that. So hence, this fact will conclude that PC must be a C linear map. Again, so this is a C linear map. Okay. And according to the construction of PC, this is unique, right? With respect to the condition that the diagram should come. Okay. So therefore, it shows that every R linear map from V to V dash. So every R linear map P from V to V dash can be extended uniquely to a C linear map. To a C linear map. This is from the respective complexifications in between their respective complexifications. Such that the above diagram. So we can view the R linear map P from V to V dash as a C linear map from GC to GC dash. Right? So we define this TC to be. So we define the unique C linear map from GC to GC dash as the complexification of the R linear map. C. Right? Okay. So TCA will be called the complexification of the R linear map from V to V dash. Okay. How are you? Since we are talking about linear maps, so if you are choosing to finite dimensional real vector spaces. So in our previous lecture, we have seen that if we are choosing two non-zero finite dimensional spaces, then their complexifications are also finite dimensional, having the same dimension as that of the underlying real vector space. Right? The dimension doesn't change under complexification of the real vector space. So therefore, if you choose any two non-zero finite dimensional real vector spaces, suppose one is P and another one is two non-zero finite dimensional real vector spaces. Okay. So therefore, these two real vector spaces will admit two complexifications, VC and VC dash, having the same dimension as that of V and V dash. Right? Okay. So now you take any from B to V dash, suppose T be a linear map, R linear. So considering a R linear map, okay, uh, from B to V dash, and we are choosing two bases. Suppose here is E1, E2, En, where n is the dimension of V, okay, and here it is E1 dashed, E2 dashed, Em dashed. So if you choose two bases in the respective real vector spaces V and V dashed, and this so with respect to this so corresponding to these bases, the T linear map the R linear map T can be represented as a matrix of order n cross n, right? So with respect to these given bases, T can be represented as an m cross n order matrix having real entries, right? That is T is actually, so suppose we are considering the matrix. So we are denoting the matrix by AT. Okay. So that is AT in this vector space. Okay. So that is AT will be the associated matrix of P corresponding to the given basis. Okay. Now, since we have already seen that the R linear map from a real vector space V to another real vector space V dash can be extended uniquely to a C linear map to its complexification, right? So therefore, so now we can consider the respective complexifications of the real vector spaces and also the respective complexification of the R linear map TC. So this is a C linear map, right? Now these bases can be Z1 into En can be transferred to a complex basis in the complexification which is of this form. E1, 0, E2, 0, En, 0, right? And also the same thing will happen for this one. So E1 dash, 0, E2 dash, 0, En dash, 0. So again, so with respect to this two bases, the respective complex vector spaces VC and VC dash, so this will help us represent TC as an M cross N order matrix. Let us call it APC. Okay. M cross N order matrix APC. Now the question is whether ATC will coincide with AP. So this is the question. Okay. So the question is whether AT equals with okay. Are these same or not? Okay. So what would be our conclusion? Now it should be noted that so if you look at the complexification of the R linear map, so TC, and if you choose, if you take any vector from the basis, okay, from this one, if you take any of these, from EK, 0. Now using the definition of TC, what it should be? It is TEK, 0, right? TEK, 0. Okay. Okay. So now suppose so if we let belongs to this, then is V1 comma V2 can be written as summation lambda k ek comma 0 by comes over 1 to n. Because the dimension of BC over C is the same as the dimension of B over R, right? As we have already seen. And therefore, the PC of V1, V2, okay? So this will be summation lambda k PC of ek comma 0, this one. So that means summation of lambda k ek comma 0. Okay. So this says that so now TEK, what is TEK? So TEK belongs to, now TEK belongs to B test, right? If you look at this map, so TEK belongs to this test, right? Which implies that so TEK can be written as summation mu j ej best, right? Or j runs over 1. Okay? So TC P1 P2 is actually summation lambda k runs over 1 to n, and TK has been written as summation mu j ej dash comma 0, where j runs over 1 to n. So therefore, this is summation lambda k mu j ej dash comma 0, where k runs over 1 to n, j runs over 1. Is it okay? So in view of this, so here you see that instead of taking any arbitrary element from PC, if we concentrate ourselves on elements from the basis, right? So you see that for ek comma 0, so TC ek comma 0, it has been written as T ek comma 0, right? Okay. Let me just take in KJ. Okay. So this is K. Yeah. Okay. So T ek comma 0, so that means summation mu kj ej dash comma 0, j runs over 1 to n. Okay. Just we are taking this one. Okay. So therefore it is summation mu kj ej dash comma j. J runs over 1. Okay. And this is true for all k of 1 to k. Okay. So therefore, what would be the matrix? So if you look at this Tk, you see that the coefficients are same here also. So this implies Tc, ATC, I'm sorry, let me denote it by ATC. Okay, so ATC will be a matrix having entries mu kj, where k runs over 1 to n and j runs over 1 to n. Likewise, if you look at this TEK, so also AT will be again mu kj, k runs over 1 to j runs over 1. So therefore, what we are seeing, seeing that, so see that, so we have seen that ATC and AT are same with respect to the given real basis on the respective real basis. Okay? Is this fine? Is this fine? So, for example, let us consider the real vector space. Real vector spaces Rn, Rn. And if you take any matrix array, so an M cross N order matrix or a real matrix. Now this Rn and Rn both will have complexifications, right? This is okay. Then using the standard embeddings, Okay, I and I dash. So what you get? AC is again an orthogonal matrix which equates with A. Right? So the complexification of A here is again A. Okay? But here this A acts on this A uh, acts on N, right? Yeah. I'm sorry, okay. So if you take A and M as 10, then you can say that this A acts on Rn, and there is complexification which is acting on the complexification of Rn, which is Rnc. But here, if you, this Rnc is Cn and this Rnc is Cn. So since M and M are same, if we choose the case to be, then you see that this A will act on Rn, and the complexification it is also A, but this will act on Cn. Okay, so that means so what I'm trying to say. So here, suppose N and M are same. Okay, and then any matrix A which has been taken here, Mn cross n R is acts on Rn. Okay, then what is the complexification of A? So the complexification AC of A is defined to be. So what would be the definition? So AC of uh, x1 x2, right? AC of x1 x2 has been defined to be ax1 ax2 for all x1 x2 belongs to Rn. Okay. Now since the complexification of Rn, this is isomorphic with Cn, right? As we have seen already. Via the isomorphism, via the isomorphism. So what will be the isomorphism here? We have already via the isomorphism. So x1 x2 will be mapped to x1 plus I. Right? So this will be the isomorphism. Right? Because just look at the situation I have already depicted the fact. Yeah. Yeah. So x1 x2 will be mapped to x1 plus I x2, and therefore so since this is isomorphic via this isomorphism, which we say that The above map, the complexification of A is AC, can be viewed in this way that it is a map which are sending x1 plus ix2 to ax1 plus ix, right? Just via this isomer. Okay? But this is a so we will say that SP this defined on that is now AC has been viewed as a map from CN to CN under this rule AC x1 plus x2 as x1 plus ix2. Is this okay? Okay. So now uh, so okay. Note that note that uh, note that A x1 plus ix2. Okay. So I'm just seeing this as a matrix here. So ax1 plus ix2 it will be ax1 plus a ix2, right? Now I can taking this. I'm just taking this I out from this one to get because A is a real matrix. Okay? So these two are same. So this does not change under this action of multiplying R with the basis, right? Because A is real. Okay. So this says that, so this implies, so since so this implies A as a matrix, as a real matrix, acts on the vectors x1 plus ix2 of Cn. Okay? And hence, with respect to this, you can see that, so you consider the complexification of Rn and consider complexification of A as AC from RNC to RNC, firstly, okay? RNC to RNC, and again, this is the isomorphism, let me just call it as phi. So this phi, so this will be Cn, this will be Cn. Okay. So ultimately what I get, so this implies that it is AC x1 plus ix. Am I correct? So therefore, this map, whenever we are considering it acting on Cn, so it is nothing but it. And the diagram follows. Right? Yeah. বোঝা গেল? দেখো, whenever we are considering the computation, that C, but actually it is A, and it is acting on C.
এই জায়গাটা একবার বলেছি সাইডে কাটা পড়ে
হ্যাঁ, ব্যাপারটা যেটা হচ্ছে, দেখো জিনিসটা হচ্ছে আমি একই জিনিসকে বিভিন্ন ভাবে দেখছি। মানে এ ম্যাট্রিক্সটা প্রথমে আমরা কোথা থেকে কোথায় নিচ্ছি ভালো করে বুঝে যাবে। আর এন থেকে আর এন, ঠিক আছে, এটা এনটা ধরো এন, ঠিক আছে। তার মানে এই যে ম্যাট্রিক্সটা যেখানে আমি লিখেছি, দেখো এই মানে এই ম্যাট্রিক্সটা আর এন থেকে আর এন এ, মানে এ হচ্ছে একটা লিনিয়ার আর লিনিয়ার ম্যাপ from Rn to Rn. Matrix, real matrix মানে আর লিনিয়ার ম্যাপ from Rn to Rn. Rn, রাইট? তার মানে এই ম্যাট্রিক্সটা Rn এর উপর অ্যাক্ট করছে, অ্যাকশন, গ্রুপ অ্যাকশন। মানে Rn এর একটা ভেক্টর নিলে আবার সেটাকে আবার Rn এ নিয়ে যাচ্ছে, ঠিক আছে। এইবারে যেটা হচ্ছে কি, তুমি Rn এর কমপ্লেক্সিফিকেশন নিচ্ছ, আবার এরও কমপ্লেক্সিফিকেশন নিচ্ছ। তাহলে Rn এর কমপ্লেক্সিফিকেশন হচ্ছে Rnc, এর কমপ্লেক্সিফিকেশন হচ্ছে এসি। তাহলে এসিটা কোথা থেকে কোথায় অ্যাক্ট করবে? আরএনসি থেকে আরএনসি তে, রাইট? এই যে এখানে যেটা আমরা লিখেছি যে এসি, এই এসিটা কি? ইজ এসি অ্যাক্টস অন আরএনসি, কমপ্লেক্সিফিকেশন। এবং কেমন ভাবে তার ডেফিনেশনটা আমরা দেবো না, এসি এক্স টু মানে হলো এ এক্স ওয়ান এ এক্স। এইবার এই আরএনসি তো অ্যাকচুয়ালি সিএন, কোন নামিয়ে এই যে এইটা ফাই। কারণ আমরা সিএন এর মানে আরএনসি মেম্বার গুলোকে আমরা রিপ্রেজেন্ট করতে পারি x1 প্লাস ix2 দিয়ে। মানে আমরা ভাবতে পারি, কেন ভাবতে পারি? কারণ আমরা দেখবো যে ওই জাস্ট ইউজিং দা ওই কি বলে আমাদের স্ট্যান্ডার্ড এফডি, আর হচ্ছে মাল্টিপ্লিকেশন কমিউটিং উইথ দা ইমাজিনারি ইউনিট। x1 x1 can be thought of as an element x1 plus ix2 which is in C. হলো? তাহলে এবার এই যে এসিটা আমি আরএনসি তে নিয়েছিলাম, এবার আরএনসি ডেসক্রিপশনটা যদি আমি এইভাবে চেঞ্জ করি ফ্রম সিএন, তাহলে ওই এসিটাই একই রকম হবে x1 প্লাস ix2 সমান, আমি x1 x2 ax1 x2। এবার আমরা লিখবো x1 প্লাস ix2 সমান ax1 প্লাস ix। কিন্তু এ যে ম্যাট্রিক্স হ্যাঁ, সেটা তো রিয়েল ম্যাট্রিক্স। তাহলে সেটার সঙ্গে ধরো রিয়েল আই গুণ করলে কি আই হবে? আর তো মিলে যাবে, চলো। যেহেতু এটা একটা রিয়েল ম্যাট্রিক্স, সেই ক্ষেত্রে ব্যাপারটা কি দাঁড়াচ্ছে, এই যে এখানে লিখেছি দেখো, a1 প্লাস ix2 হয়ে যাবে ax1 ax2, এই যে এই জায়গাটা। তাহলে x2 টা এটা যে তুমি তুমি গুণ করলে হবে, এটাই আলটিমেটলি তো কিছুই হবে না। আই আইটা হচ্ছে যেটা যেই লিখতে পারলাম, তার মানে আলটিমেটলি তোমার ওই ডেফিনেশনটা চলে এলো, যেটা হচ্ছে অ্যাকচুয়ালি AC x1 plus I. And this is true for all these elements. A or AC as a map, description কি জানাচ্ছে এসিটা ছিল আরএমসি থেকে আরএমসি তে আরএমসি এর উপরে হচ্ছে আর এই ম্যাট্রিক্স অ্যাকচুয়ালি পিএনএল অ্যাজ এ ওয়ান, ঠিক আছে, এটা অ্যাক্টিং অন সি সিএন, তো মানে সেলফটা এটা, হ্যাঁ, যেটা কমপ্লেক্সিফিকেশন is just the same matrix A, but it acts on CN. আগে আমরা যেটা ভেবেছিলাম যে ওই এটা আরএনএ অ্যাক্ট হচ্ছে, এখন আমরা যেটা দেখতে পাচ্ছি যে ডিএনএ অ্যাক্ট হচ্ছে, কিন্তু কিভাবে অ্যাক্ট হচ্ছে সেই প্রসেস, ঠিক আছে, এ এক্স টু এইভাবে অ্যাক্ট হচ্ছে। দেখো বোঝা গেল কি? Yes. So this is for number 2. So any so so a real M cross N matrix thought of as an R linear map from Rn to Rn, right? Matrix এর নাম দিতে পারো A. So this is so A is a map from Rn to Rn. So it can be viewed as a C linear map.
স্যার হ্যালো, হ্যাঁ স্যার বলছি আমাকে না একটু বেরিয়ে যেতে হচ্ছে। হ্যাঁ
হ্যালো
হ্যালো স্যার, শুনতে পাচ্ছেন? বলছি আমাকে একটু বেরিয়ে যেতে হচ্ছে।
হয়ে গেছে আমার, হয়ে গেছে।
আচ্ছা আচ্ছা আচ্ছা,
বলছি হয়ে গেছে আমার,
ঠিক আছে স্যার।
2 মিনিট, এটাই শেষ করছি।
হুম,
Can be viewed as a linear map from Cn to Cn. ঠিক আছে, এটা হলো in a natural way. Natural way. Okay, so this one I would like to end. ঠিক আছে।